And this particular system is not very unknown to you. In fact, if you look around, I was just looking at the list of the participants, and I see that the participants are from Far East, Assam, and then we have this side Gujarat, and then we have Punjab, Haryana. People are from Kerala, Tamil Nadu, Maharashtra. You name Odisha, Bihar. So I can see that this particular hydropower system, if you look around yourself, you will find that there are some hydropower plant nearby. So this is not a new technology. So I will be a little rapid because for many things you may be knowing it, and I'm using a lot of graphics. I would request that you should use your, when we talk about question answer, I'll give 15 minutes for the question answer. So please do not hesitate in asking the question at that time. And so I'll be running. Hydropower is a proven renewable, mature, predictable, highest conversion efficiency. There's no other energy technology which can compete, which is even nearby to the efficiency what this has, and competitive renewable energy source in terms of cost economics. Hydropower requires initial investment, but had the advantage of low operation cost and long lifeline. A hydropower plant can have a life of 100 years, and in fact, there are plants which are still having 120 years. Like in those people who are from Bangalore or Mysore, they know that they're very close by them, which is operating for the last 118 years. 118 years. Hydropower often is a part of multi-purpose project, and at the moment it's about 16% of world total electricity, and about electricity for renewable energy. And HP plays a key role in power system due to its flexibility and reliability. Those who are electrical engineers, they understand what is flexibility and reliability means. There are a lot of ancillary services, and there are a lot of peaking requirements and ramping requirements, and those all are served by hydropower. It can support the penetration because right now there is a big trend of renewable energy penetration, especially the solar. It can always provide because solar is the one which is totally, first of all, time bound. It is not available not all 24 hours. It is not in the same intensity everywhere, and also it is not same time even in the daytime. It is not in the same intensity. So it requires a lot of grid management. It requires a lot of storage management. So regardless of size, it can give an opportunity for local, national, and regional development. So in fact, there are many countries which has got majority of. In fact, there is a country like Norway which is almost 98% if solar. So there are many countries which has got a largest share which is from hydro, but not of course India, because India is still has a requirement is very huge and the potential is not that high. Hydropower is unfortunately being overlooked by the energy policy in the energy policies. This is very unfortunate. Though hydropower is so attractive, but it has been because of reason that it takes a lot of time. Its gestation period is quite long. So politicians, bureaucrats, and the policymakers, for them they want quick results and short-term results. And for that, hydropower is not a short-term player. It is a long-term player because it also has a long life. You can have a solar energy system. You can have any system which can come in very quickly, but it has a relatively lesser life, shorter life compared to hydro, which is 3-4 times the life. Life cycle analysis of hydropower shows that it's the cleanest energy technology with the lowest carbon footprint. Not only low, I would say that one of the lowest carbon footprint, and it has got a highest energy payback ratio. This is a new term which you might not be knowing. What is energy payback ratio? That means how much energy you have used in constructing or operating that plant compared to what energy you get it. So I'll be talking about that. Hydropower is derived from the force of energy or moving water from higher elevation to lower elevation, and it is being used for irrigation purposes, water mills, textile machines, sawmills before the formal electricity generation started. Mechanical power of falling water was used by Greeks. In fact, if you look at that in terms of using water power, first hydroelectric project plants in terms of came in 1817 in England. Then it has come in something, but finally, where we have the industrial as well as residence load, which came in 1882 in US, a place called Appleton, Wisconsin, which is 12.5 kilowatt. in September 30 and 1882. So this is our history-wise, and in terms of in India, hydropower. If you look at the history of the hydropower, you'll find that history of hydropower started with a small hydropower. Small hydropower, those are the small size in terms of megawatt. Today we're talking about 1,000 megawatt, 2,000 megawatt, 500 megawatt. I'm talking about kilowatts. So like 130 kilowatt, 2,000 kilowatt kind of things, which is the during those period. And the reason is those days transmission lines were not there. High voltage transmission line not there. So it used to be that you use the electricity, I mean generate electricity and use it there itself. So there was hardly few places where, and if you have a very long transmission line, there are a lot of losses, and those things were there. So if you look at can we mute him? Can we mute? Yeah. So you can see even those were in the hilly areas, Darjeeling, Mysore, Missouri, Simla, for that matter, even in Sonapani, this place called Shillong, and in Kashmir there was a project near Baramulla. So all these projects, but the fall-based, canal fall-based project came in 1930-25. Actually, the first project came, and these projects came in nearby Haridwar. Then it came in Lahore. It came in Jammu. So those of them when canal were built up very strongly. In terms of data, we talk about the first hydro project I just mentioned to you, 1897, first major hydro station, which was actually initially it was 2,000, but today it is 54,000, 54 megawatt. And first private hydropower station came in 1915. Largest tunnel diameter is 15-meter dia. Longest tunnel is 27 kilometer in Napta Jhakri in Himachal Pradesh. Highest dam is Tiri Dam, which is 260 meters. It's made in Earthfill Dam. Then hydropower capacity was very small, 508 megawatt, but today, if we talk about 45,000 megawatt, and the largest capacity project in India has been so far 1,500 megawatt, and I think it's a 2,000 megawatt is coming in Arunachal Pradesh on lower Subansiri level, but worldwide, the highest project size of 22,500 megawatt in China and 1,400,000. You will be a little bit surprised. Even the project of Brazil, which is 14,000 megawatt, has got more than 10% more generation than the capacity of the Three Gorges. Three Gorges is almost 50% more, but in terms of electricity generation, so it has got a very nice plant load factor, utilization factor, ATAL. In terms of journey, this is the journey of electricity. I can see recent time. This says the gradient of development in hydropower is very, very slow. And the reason has been that there are, first of all, opportunity in renewable energy are coming more, because for the policymakers, for financing, that's relatively faster. And can you mute, please? Can you mute, please? All, please mute. Rhythm, can you mute all of them so that the class is not disturbed, please? Okay, so this is where potential lies. We have about 145 gigawatt, and another 20 gigawatt is from 25 gigawatt for the small hydro, but we have only used 45, and plus the small hydro, which is 4.5, so roughly 50 gigawatt we have done. We have 200 power stations in large, 710 units, including 9 pump storage. There are 36 projects of 12,000 megawatt are in the project. There are multiple projects. There is storage only. There are run of river. There are this size, and there are surface power. So a lot of hydropower plants are underground. And in terms of ownership, for the large hydropower plant, most of the time electricity, they are owned by government body like central government in the form of NHPC, NIPCO, BBMB, TSDC, and those things. And the state 60%, and private. So private in large hydro is relatively small player, but in a small hydro, it's major player. So this is just to give an idea. In terms of policy, there have been policy declared. First of all, let me tell you, the hydro subject does not belong to Government of India. The hydro subject, since it is using the water, hence it is a subject which is belongs to the state government. So hydropower scheme, if it has to be developed, it has to be developed with the consent of or with the approval of state government. So this is one of the things. And as you know, state government has own politics and dimensions, and but central government, since when the two interstate issues come, the central government has the power as per the legal treat. So they have the policies. They declared the policies in 2008, the recent one, and they also issued the policy of tariff. But I would like to say state government still has the power to overrule it. And but you had to convince, you had to counsel. So you had to make a lot of negotiation with the state government between two states especially. So, and some modification has been done. Then one of the things when there, that now you might have heard renewable energy purchase obligation, RPO, where a distribution company or a user company necessarily buys the renewable energy. It's called the renewable energy purchase obligation or RPO. So you have to buy renewable energy even if it's expensive. So same thing. Now hydropower purchase obligation has been reduced. That in addition to though hydropower is also renewable, there is no doubt about that. But since hydropower still is a very large share, it used to be not considered earlier for 25 megawatt or above especially. But now since being considered as a power, so it has made a separate issue on that, the hydropower purchase obligations, and also some kind of grant for enabling infrastructure. This has been there, and some grant for flood moderation and policy for promoting cross-border tourism, cross-border trade. This is just an example here where I put in hydro here and I put a solar here. So we talked about capital cost. Capital cost, of course, today hydro is expensive in terms of capital cost. But in terms of overall economic evaluation, if you look at that, then it's much, much better. Even the solar radiations, the greenhouse gas emissions are much more for solar, because the electricity which is used in making the cells, it is still the coal-based electricity in Russia and China. So, and if you look at that loading, this is government policy because it gives a lot of concessions. There is no transmission charges, there is no free power, there is no local development, there is no wheeling charges. And so this is where I would like to say that there is a lot of unfair concessions to promote solar, or even hydro is renewable, but those concessions are not available to hydro. So this is a little bit policy issues, and which you may not be involved, but you must know about it, that what kind of policy unevenness is there. You might have heard a small hydro word, also a small hydropower, which is nothing but in terms of size, scale, like 20,000 megawatt or 100 megawatt or 50 megawatt, 25 megawatt. So, but that's where a small hydro in India, we can, any project which is less than 25 megawatt is called a small hydropower, and are often but not always run of our schemes, but it's installed in existing water infrastructures like barrages and dams and irrigation channels and locks, and these are also located close to the villages to serve the users, even if it is an isolated systems or it could be through the grid system, and it has a high level of local contents. In fact, most of things are in terms of Atmanirbhar or in terms of local indigenous manufacturing materials, and it also uses a lot of local materials. So it has got almost 30-40% of project cost goes into local economy. These are the classifications worldwide in terms of small hydropower. So you can see some people like China calls the small hydro 50 megawatt, Cambodia calls 15, Sweden calls 15, India calls 25, Norway called 10 megawatt, UNIDO and Brazil called 30 megawatt, USA called 5 to 100 megawatt. They have different definitions in different places. Japan is 10 megawatt. And also within the small hydro, we have 5 kilowatt pico, micro, mini, small, medium, large, etc. So that you can understand that it is basically scale. And this scale is not a sacrosanct scale. This is a scale has been done basically for promotion, for providing some promotional activities. And for that reason, these definitions are there. But hydropower is a continuum of the project. All of us know that where hydropower lies. Hydropower does not lie in the groundwater. Hydro lies in the surface water from higher elevation to lower elevation. So these are the areas. If we have mountains, we have hills, like even in southern India, on the Western Ghat side, we have a good hills. Those hills are very good for hydropower, and there are a lot of hydropower plants on that area in the northeast, in Himalayan. But when the water comes from, like for example, Punjab, though Punjab is a flat area relatively, but then water comes from Himachal and Jammu Kashmir. So that water is being used by the plain areas, and then they use the canals. And in the canals, normally, since canals use very mild slope compared to the topographical slope, so there are some falls. And I'm sure that all of us must have seen the one or two or many canal falls in their life, and sometimes even movies have that kind of thing. So these are the area where the hydrogen cycle. So this cycle varies every year, but in terms of quantity of water, it is a fixed one. So it's just like you say, there's the ocean, then it has evaporation. So this hydrogen cycle, so it follows hydrogen cycle. In terms of potential, it's very simple equation. All of us know this. We have gone through in class 9th when we started physics in a very chapter factor that power. This is like work done. The rho is Q and H 9.81, and efficiency. The eta is efficiency of the turbine gearbox generated together. So all that will become. And if I just keep a density of water as 1,000, so that I can convert into watt into kilowatt. So the equation becomes very simple equation, like power in kilowatt is becomes QH. And if I take an efficiency of say 0.8% or 80%, and if I just take it as an assumption 10, so it becomes 8 QH. Simple, very simple equation to find out what kind of potential we have. Of course, we can do more fine refinement. Similarly, if we have a flowing water, kinetic energy, this is where we have head, where there is a water level difference from upstream to the downstream. But if you have only a flowing river where we have a velocity, we call it kinetic velocity and or flow velocity, then it works similar as we have wind energy, where we have a sweeping, power coefficient, and then what kind of area through the turbine passing through. So this is what happens. All this. Gross head is the vertical distance, not the longitudinal distance, but vertical difference between open surface upstream and downstream. And of course, we had to also reduce the losses which happens in the water systems through the trash rack, pipe friction, bands, valves, and of course the exit of that. So all that becomes my losses. So when in this equation, the head is not the gross head; it is the net head. So a net head. So that means I had to reduce from my gross head the losses, and that becomes my net head. So this is a very simple. All of us have gone through in our classes and our schools and our. So these are the efficiency of hydropower station equipment. Hydropower could be an efficiency multiplied by generator efficiency or gearbox in some cases. Not in all cases. Please understand, gearbox is only in those cases where my the turbine rotations are small and generator rotations are high. The speed of generator high. So we have to match with them through the gearbox. And this is the way we can reduce the cost of the generator, because if we have a higher RPM generator, they are less expensive compared to a lower one. And moreover, lesser than 600 RPM, you have to tailor made. You have to tailor made for them. So if you have tailor made a generator, obviously it will be very expensive. So generator efficiency in small hydro is, for the small one could be 96, but for the bigger projects, it could be 99, 99.5 also. The gearbox very efficiency, and in fact for the turbine efficiency can go even up to 95% very easily for the large turbines, because their stakes are high, so cost wise down. In terms of topology, the classification is based off hydropower by a purpose, single purpose or multi-purpose. Like there are many projects, I'm sure that many of you know that there are multi-purpose, like Bhakra Dam is a multi-purpose project. Flood protection, power generation, irrigation, drinking water, like that. Similarly, there could be single projects, which is like Lapta Zakri is a single purpose project, only power generation. Types of project: runoff river, reservoir based, interstream, pump storage. By size, we can have large, medium, small, mini, micro, pico. By head, we can talk about high head, medium head, low head, or ultra low head. Ultra low head is less than 3 meter. By system, we can isolated system or off-grid system or connected to the grid. We can have regulations. We can have the daily kind of storage or weekly kind of storage. We can have seasonal storage. We can have multi-year storage. And also in a river, we can have a single project or projects in cascade, one after other. Runoff. So just to give a very quick overview, that runoff river schemes where water we are diverting So we are taking the water runoff from the side, and then and the storage-based schemes, canal fall-based schemes, Varad or in stream, and pumped storage schemes. So very quickly I can show you that like this is a river. I'm diverting the water and bringing through the water channel, and this is a powerhouse. I'm sending back the water. So this is a simple type of water, and this is a schematic, or this is the actual picture of a project in Himachal Pradesh, Chamba district. So this is where you can see this is very simple run of river schemes, and here I have heads are very high, and so, the discharge is relatively low. We have such kind of a scheme. This is in Kullu district. This is in both are in Kullu district, and even ownership could be anybody. There are very simple structures to do that. And this is the project which I can explain that is a 1902 Siva Samudra project. Those people who are from Mysore or Karnataka, they should visit this power plant. And this power plant, this is the power plant, and this power plant does not have a road till date. They don't have a road to go there. So they use, in fact, the trolley. This is the trolley. They use it for going there. And this project was built in 1902, 118 years back. So it still is very nicely done. And this project is right now under renovation. The turbines are being replaced. So this is in terms of example, you can see this is in terms of technology worldwide, it's the same, whether it's in southern India or it's in Switzerland. So I just give an example of two, whether north hemisphere, south hemisphere, anywhere, technology is same. We use the water of the river. That's simple. So that's very simple way to do that. These are the canal falls. You might have seen small canal falls where we divert the water, put the powerhouse, bring the water back to the river, back to the canal. These are normally very small heads are there, 1 meter, 2 meter, 3 meter, 4 meter kind of thing. And I'm very sure that if you go to canal falls, you will see some kind of projects. Those people who are from any place, I like to say, because canals are everywhere in India. Canals are everywhere. I think relatively canals are very less in Kerala. But if I talk about all other places, canals are quite a lot because of agriculture, agronomy is our one of the economy. For that region, this is we have a lot of canals, so there is a lot of potential there, and they are very easy to do. Similarly, if you have built up a dam, incidentally, India has more than 5,300 large dams. So almost 10% of large dams of the world are in India. So India is very that way quite good that we have a good. We constructed a large set of the dams. Basically, these dams were built up for the purpose of irrigation, drinking water, etc. And so this and water is released for irrigation. So these are the give opportunity. Many times they have not been used for power generation, but in the recent for last 25, 30 years, there have been a lot of projects which are coming up where they are using this outlet of the water, which is going for simple drink irrigation. They're using it for power generation. So such examples are here. This is a Bargi Dam. These are the kinetic turbines. You can see this is what you are putting turbine right in the water, and this is like a wind turbine. You can see here. So here only media is water and flowing water, like flowing wind is there. So velocities are not very high, not like wind velocity, and here, but since it is a mass, so it gives you electricity. So this is another way. But I would like to say today, a lot of research is happening, including my colleagues are doing in our department. But it's of economy of is still yet to be established. There are more than 70 laboratories in the world. People are working. I think US Department of Energy has spent a lot of money on this, and they have a lot of examples to do that, but still it takes time. So these are some small turbines are there. Another emerging area for the research and the work, and which is long awaited, and I would say that right now there is a thinking on that to use a pump storage. The pump storage is not the way of electricity production. It is just only a management of the storage, like storage, the word is storage. So what I do is I store the electricity by way of lifting the water. I lift the water on the top of the hill or anywhere on the top of the reservoir or top of the hill. And then that is whenever I want to generate electricity, I just simply allow the water to flow from higher elevation to lower elevation through a turbine. The same set of the units can work. In fact, right now, you need not to have two sets of like pumps separately and turbines separately, because their hours will be different. Generation hours in the grid, since every system is connected to the grid, hence their generating hours will be different. Their generation cycle will be different. So you require power when you have peak power requirement, and when you have off-peak power, which is available, nobody using it, even from thermal power plants and others, that power can be stored back to the one. So this is here happening, and there are many projects which are coming on this scale. And you can see this is like a very schematic way given here, that I'm pumping back the water here. So I need to have two reservoirs here, very simply. And then when it's generating the water flow here to here. This is a schematic for Teri Dam, which will get commissioned, I think, by 2020. 1,000 megawatt project, which will enhance the generating capacity, also the management of the demand side management or generation management in that sense. There is a big need in India for this, because the power system operation is right now in a big shift. Because earlier, all those things used to be there, where you have the base load from coal-based plants, and then peaks used to be from hydros, dam-based projects. But now, since we have large-scale variable, and those are considered to be must-run, because we have to use them to bring our carbon footprint low. So my power generations, right now, my power generation, which was controllable, right now it is becoming low, was following non-controllable one. But now we are having power generation is no longer fully controllable, because solar and wind is not that kind of controllable. So pump storage are one of the best partners, and these are the commitment given by the government of India that they require. They proposed this kind of plants by 2030. So there's a good scope here, and there's a good scope for storage. All of you have seen, and if those people who are interested in power systems, they might have seen the news of April 5, when Prime Minister has declared that for 9 minutes the people should switch off their lighting. I'm saying that, and that was a big challenge to the power system operators and all these things, and they have done job very nicely. But that job has been done by the hydropower. Most of that variation in the generation and ramping is called ramping down and ramping up. Where we are in the shortest possible time, you are reducing your generation, and in shortest possible time, you are increasing your generation. So 18,000 megawatt hydropower has been supported by, out of the whole 31 megawatt, has been supported by the hydropower. So hydropower is done, and that because you could ramp it so fast. Ramping of hydropower plant is in 30%, 40% per minute, 50% per minute, compared to a thermal power plant where ramping will be, if you are even having 1% of ramping per minute, that's too good, very good. In fact, people have only 5% at the moment. So right now, regulators are asking them to make it at least 1% of ramping, but ramping is not that easy. So people have seen that wonderful of hydropower. Today, hydropower is also can give you 24-hour integrated approach with PSP, because PSP is a large storage of energy, large. So we can talk about that. We have PSP, where pump storage can give you a 24-hour supply. There have been a lot of tenders where private sector has jumped into, and there are a couple of plants where private sector is now going for 1,200 megawatt kind of power plant in integration with wind and solar in Karnataka and Andhra, and they are bidding for guaranteeing like a US UPS kind of things they're giving. So today, all of us, since all of us are teachers, you can think of coming into this area where the pump storage has a lot of issues in terms of grid management, in terms of their, because when you are having pump, you have to have a reactive power. And for that, you have to use condensers. So there are issues that when you go through all those, you will be able to appreciate that. Just to give an example that worldwide, hydropower is considered as a renewable from long back by all world. It's only India 2019. I had fortunately had a opportunity of leading an international group for IPCC report. IPCC, all of us know that Intergovernmental Panel for Climate Change, where they have brought in a special report on renewable energy. So this is just to give that. It was a opportunity where all of the world, the people are working on the hydropower like that. Now, so far I talked about the policy part of it. Now I'll be talking about this new things, evolution of thinking. Good old days, 1940s, 50s, engineers used to dictate the things. Okay, hydropower. Engineers say, okay, this is a place where we can have hydropower plant, and then let's do it. Bhakra was one of them. Mahatma Gandhi in Jog Falls was another one. There are many such projects. But over the period, economists also started thinking, whether, because there are other type of technology came, there are other type of energy technology came, the economists said whether hydropower is economically viable or not. People started talking about. Then from 70 onwards, environmental issues came into picture. That whether environment should be right or not, and thereafter the sociologists came, the settlement issues came. Most of the projects like Narmada project in in Gujarat, in Tehri Dam in here, in Uttarakhand now. So the many places all over the country, all over the world, these issues came up very strongly, and which has resulted because people were earlier only engineers used to think about hydropower plant. But today there is a battery of people, and so this you have to deal the subject very differently. And not only that, you also have to think today, not only this in terms of environment, but also you have to think of what is happening to the upstream and downstream, whether fish or soil erosion. And those people who are from Assam, they know they have blocked. Some of the people have blocked for last 6 years. Lower Swansea project, and they had an apprehension that project will give them the bad thing, which was so today you have to manage everything. So that kind of evolution of thinking happened, and also greenhouse gases. Nobody used to bother about greenhouse gases earlier, but now greenhouse gases, if they are coming from hydropower plant, please understand greenhouse gases come from everywhere, including all our. But when you do hydropower, people are after you, not because for irrigation they can't do anything. So these are the zones where biodiversity issues coming up here. So people are talking about these terrestrial flora and aquatic flora and fauna, terrestrial, avian, and aquatic fauna, all are important today. So we have to take care of it. And these are the sustainability sensitive issues: hydrological regime changes, reservoir creations, water quality changes a bit, and sedimentation, biological diversity, barrier for fish migrations, involuntary population displacement, affected people, public health, cultural heritage, and sharing the development benefit. I would like to say here, in the recent policy of Government of India, the 2% of electricity production shall be shared, is being shared by the people who are project affected. So this is a major change, and that is a game changer in terms of those people who are nearby, but still there are still issues. These are the, this is a auto taken from the report only for that, where the carbon emissions, GHG emissions from hydropower, you can see they are one of the lowest here, one of the lowest, not others. So this is, you can see, this is another one which talk about IPCC, not only 2011, 2014 report, AR report, the IHA report. So this you can see, this is my 18.5. You may be wondering, the solar is greenhouse gas emission. Yes, because soil while generating does not emit, but while its cells are manufactured, that has a lot of use of the coal power. And so for a life cycle analysis, we had to account for everything. And also for disposal, you have to require a lot of power. So all that philosophy there. So this is energy payback ratio, that how much energy you are using while constructing it, and how much energy you are generating in its life cycle. So if you can see, hydropower is the outlier. Nobody can match that kind of things with the hydropower. So this is a very outlier. But Resource assessments are there, run of rivers, storage projects, existing dams, so water storage sections. There are opportunity available, residual potential in pipelines for drinking, industrial use, effluent outfall at water treatment plant, sewage treatment plant, hydrokinetic in flowing channels, small scale pump storage. So these are the one which has there are resources available. There are a couple of methods of hydropower assessments where you can do conventionally. They use the maps available, discharge, published records, field measurements. There are so those things are happening now with the GIS and remote sensing. These are things are coming up, so they are being used. There are softwares available. There are software with GIS. There are interactive web-based software, and they are design, conventional design, software-based tools. So these are the new thing over there. So with a GIS-based application for assessing small hydropower potential or hydropower potential, sorry. So there's a river network potential at. So these are some of the names which are there. Please understand, when these names are there, they are such country specific. They are not. They are not good for universal applications. But for those who want to go into this, for them this is just introduction there. Similarly, there have been tools for assessing the river discharge, etc. So these are the, you might have seen, this is many students use this red screen, which is from Natural Resource Canada, which gives a preliminary analysis of this. This is one of the a popular software which is available in public domain, because most of the others are not in public domain, and so this is the people use it. This is so just trying to tell you, because I had to cover everything in the hydropower of this in this particular hour. So here you can see this is my catchment here, where the water is flowing from this higher elevation to lower elevation. And if I divert the water from here, so I am using only this much catchment. But then there's elevation difference, so I can put the power plant here, I can put power plant here. So that whatever I can put into single, I can put into multiple cascades. So you can just see that level difference are there. So I can divert, and this is the way I delineate the catchment, and I will be able to find out my potential over there. Then I need to verify ground verification. I need to locate where the powerhouse can be there. I have to locate where I can put a diversion weir or a barrage or a dam. I have to see what kind of head is available and what kind of discharge available. Please understand, discharge is not constant. Discharge varies. And especially in India, discharge varies so much. Like, for example, in monsoons, you have so much of water, and after monsoon, there is no water. So especially in those places which are not have an advantage of snow melting, they can see that, especially in Maharashtra, many rivers are there for 10-meter high deep, and suddenly after monsoon, there is nothing there. So those kind of things happen. So they were deceptive, and those discharge should be measured, and you have to see that on such kind of variation, you need to store it to regulate it. Like many of you might be using the pumping the water during for their, when they use the water come in the morning only for 1 hour. So what they do, they store the water on the top of the house, and then you use 24 hours. So similarly things can be done. So that for that region, dams are mostly in those areas where the water availability is low, and water availability is in for few days or few months, like in central India and southern India, and some part of East India also. But most of the time in those areas where water is available around the year, storage is not that much. So that is where I would like to make it clear on this. So these kind of master plans, you can prepare them. You can see these are the potential sites. So clustering you can do. So when I say clustering, that means when you do you can try to develop all together, so that your overhead cost, your transmission cost, your road cost is all shared. Much simpler one. Similarly here, this is like a very hilly area. Arunachal Pradesh is one of the most potential area for hydropower plant. And this is Punjab. You can see even in Punjab, canals are there. So on the canals, you have these kind of project potentials. And I would like to say Punjab has done very well on this, developing these potentials in both government sector as well as private sector. So this is Narmada River. So there's a lot of sites. You can see the gradient of the river is rapids in the beginning when it starts from Jabalpur, etc., and then later on when it enters Gujarat and Maharashtra. So somewhere it's related factor. So these are a lot of potential sites. Even sites like Ladakh. Ladakh is a place where you might be wondering that in Ladakh also hydropower. Yes, there is a water flows there, and there are areas where you can put the hydropower plant or the river. Of course, they will not be very high head, but these are the place where you can put hydropower plant here easily. And these are the been clustering there. And right now there are 34 power plants which are under construction. Many of them have been commissioned. So Kargil and Leh, that's Ladakh area where people used it. When you have to develop a hydropower plant, it's not a small hydro, because it's a hydro project. There are administrative issues, there are pre-implementing activities, there are implementing activities, and post-commission activities. So in terms of pre-implementing activities, administrative activities means that you have to advertise sites, you have to give the license to somebody. Even a government agency has to take a license from state government. Please understand, when I say administrative, there are even suppose a government agency, like for example, then they have to get the approval. They have to get the approval from the state government. Any state agency also has to approve by the government. I hope you understand the difference between agency and the government. Government means secretary and that department, and agency means like Power Corporation or Jal Vidyut Nigam or Hydropower Corporation, like that. So that's makes the difference. So they give the permission to the government agencies as well as the private agency. And of course, in private agency, they have to give in a transparent manner. So they do normally bidding for kind of things, and they have to agree assignment, and pre-implementation activities comprises of preparing the investigation surveys, reports of different stages, approvals by the state government or central government, depending on the size of the project. Those projects which are 1,000 megawatt, 1,000 crore and above, will go to the central government, central electric authority, or interstate issues will go to central electric authority, and rest will be dealt by the state government. Then there are land acquisitions. Land acquisition also, forest land is a tedious process because it takes a lot of time. Civil land is relatively easy, and private land also is easy, but many times in private, local politicians try to exploit. Clearances for environment, power purchase agreement, clearances from different agencies, preparation for plan for research, rehabilitation and financing. So all these are pre-implementation activities. And after that, when you do everything, all this, you start constructing, and then you do. These are the reports which are prepared. Readiness level report, pre-feasibility report, or it has got both names. Some people call it readiness report or preliminary report or a pre-feasibility report, PFR they call it in short. And then detailed survey investigation, then feasibility report, detailed project report. Many of you might be confused that feasibility report and detailed project I have placed in one. Yes, in India, detailed project report is more common to be spoken, but actually it's a feasibility report. Internationally, it is called feasibility report. So somebody talks to you, oh, you have a feasibility report, that means he has a detailed project report. So all the content of feasibility report and detailed project report are the same, except India, Nepal, and that's it. There are two countries only we talk about detailed project report, otherwise globally it's called feasibility report. Then engineering and construction report and as-built report, because when you do the engineering and prepare the construction drawing, many times you make a lot of changes in the structure, and that is very rare. So these are some surveys where hydrological, topographical, geological, power load demand, socio-economic, meteorological, environmental, construction material survey, power equation line survey, mud disposal survey are to be carried out. And then you have to do the topography and geomorphology of the site, evaluation of water resources, site selection, basic layouts, hydro turbines and generators, environmental impact assessment, economic evaluation of the projects and financing potential, and institutional format and investing procedure. So it's a big work. It's not a simple work. So if you look at the activity wise, there are a lot of disciplines. If you look at these all activities, I've placed it here, you'll find there are a lot of disciplines involved. You have a civil engineer, you have electrical engineer, mechanical engineer, electronics engineer, computer engineer, financing man, legal man, social man, environmental man, politics also. So all that is required, and this is a way. It is a highly multidisciplinary. Hydropower is a highly multidisciplinary. Now let's look at how the procedures. The discharge is to be measured, and discharge can be measured by the direct method, indirect method. I'm not going to very deep, but it's just to give you, there are various methods to make the discharge. And because measuring many times we don't have the discharge data available, so you need to measure the discharge yourself, and for long term, not for at least not for one day, many days, many months, or many years. So just to give an idea that what I will do, that this is the data which we have collected, say for example in meter cube per second, and because discharge data which varies from January to December, which discharge I should take for my power generation, for deciding that that powerhouse will be built for that discharge. So for that reason, I'm mentioning about it. So you can see here there are variation from 2.94, 2.95 to 10.1, so which one I should choose? So if I do it, I put in descending order, and then I try to make a curve here. You can see here, if I use a, suppose I have a head or some kind of head is available, and then if I have a potential of electricity, so if I use a very high level of discharge, then potential can be 12 megawatt. If it is a low one, when it becomes 3 megawatt. So if I see, you can see here which one I should choose. Whether should I 4 megawatt, should I choose 7 megawatt, which one I should choose. So I have to cost economics, which is more economically viable to me. Please understand, if I had to supply electricity 24 hours, 365 days from the same plant only, then I have no other option to choose this one. But where my system is part of a grid system where a lot of multi technology are coming in, so that I can think of using this 7 megawatt. So this is the things which has to be very clearly mentioned here. You can do alternate layouts here. You can do this layout here, here, whatever layout you want to choose. You can also use the existing dams here, etc. Can you?
Sir, you are not audible.
No, because I kept myself mute that time. I said 1 minute, 1 second, because there was something, somebody knocked it. So okay, now I'm audible.
Yes,
Yes,
sir.
I
Yes.
hope. Yes,
Yes.
very good.
Yes, sir.
So these are the plant you can see there, whether the concrete dam or earthfill dam. These are the low head schemes. You can always do that. And there is another possibility, like if you have a open channel, I can go along with the contour of the area, and if you don't want to go that, I can puncture it. I can make a tunnel. So all kind of possibilities are there. I can do a typical layout. I can take water from the right bank. I can come back on the left bank and go on. If there is a land issues over there, otherwise I can take this canal right from here. You know, but sometimes issues comes here, so I can go this side. So I can keep on, moving like a road. I have to just see what is economical, and how the land is available to me. So in terms of technology, there are components. So far I talked about policy, and planning purpose. Now I talk about technology. There are civil works, there are equipment, electromechanical works, and there are transmission. So everybody's here. So in the civil works, we have diversion weir, power channel, desilting tank, four-way tank, or balancing reservoirs or surge tanks, penstocks and anchor blocks, bypass arrangement, spillways, power building, and railways. And electromechanical equipment, we have turbines, generator, governor, gearbox, control panel, all those things are there. Then auxiliaries and transmission distribution will be there, power arrangement. We have a switch yard, then we have, switch yard, from there, power is evacuated. So everybody comes sit here. Diversion structures can be of various types, where we have also not only the main body, we also have a spilling because it's in the river. So we had to pass through the flood. The energy dissipation arrangements, fish passes, because right now we can see that fish migration, especially because most of the time now this concern was not there earlier. Though there was technically it was there, but it was not that much big concern. But today that big concern is there, because fish is the one which actually indicates the even water quality. And fish is the one which also brings a lot of aviation. Avia means birds. So fish is one of the very good indicator of environmental condition of the river. Residual flow arrangements, you also see that there is environmental flow, which concept has come recently. In the water canal systems, you have to see the intakes, canals, pipes, tunnels, penstocks, etc. Based on that. And the headworks, I have to see that sediment load is not drawn by the canal or tunnel. The passes flood or pass safely. Those people who know that debris are there, a lot of debris comes along with the water, and also ice. There are many areas where ice formation takes place, so the ice should not disturb, or I should take care of it. There is sediment control at the intake gate, so that I don't take the sediment along with the water. Too much sediment, some sediment certainly will go. Then I have to see settling basin control. I have to make it that weirs can be various kind of things. Barrage or weirs can be of various types: trench weir, rock fill weir, vertical drop weir, concrete weir with sloping glacis, conda weir, inflated weir. Those 2-3 weirs you might not have heard actually much. Many people might not have heard conda weir and rubber dam. So these I'm introducing you. This is a trench weir with a drop weir. It's also called tyroline. This is called drop or bottom intake, where I put a trench in the river, and through this trench, I am withdrawing the water. So my river bed slope does not get disturbed. So only I have the bottom wreck where the water, but this water will also bring a lot of sediment. So this has got one advantage, that it does not disturb the flow, but also it brings a lot of sediment. So I have to make sediment more clearly there. So these are the vertical drops kind of structures. This is like you have a trench weir I just mentioned to you, which is also called tyroline. This is a coinda. Here you can see it is like a trench weir, but it has got like a slide, children's slide kind of things, where advantage it has got a lot of wires, very thin wires. I mean, not thin, they are very small gaps are there. So only water enters, but sediment does not enter. Because of sweeping action, whatever the solid part comes, it moves down. So this is one of the way, but I would like to say in India it's not very popular. It's only few places people are doing it, but this is also one of the way as a technology. Inflatable weir, we can use the inflatable weir. We can use the steel gates. We can use the rubber gates, etc. As you can see, these are the rubber ones, and we can use the fish passes where we have ramps or some kind of arrangements so that fish can go. Even the people have used in some places the lift also. The channels are various sections: open channels, rectangular, trapezoidal, triangular, closed conduit, can be of PVC, steel pipe, GRP, HDPP, reinforced concrete pipes, and alignments has to be there so that it is possible with the shortest one. And material can be used in terms of lining, stone masonry, concrete lining with LDP, shotcreting, brick tiles, RCC. These are the sections which are very common. And this is the equation which normally use it to find out the sections, how much section we got. So if you know the discharge, if you know the discharge, if you know the kind of materials which are using, if you know the slope, because slope is the one which geometrically you can decide, I can find out my section. So this is especially if any civil engineer is there in the class, they may know very well it because they have done it all through their system. These are the geometric sections, as I said, that in terms of finding of the calculations. And we also have the desilting arrangements where silt can be desilted easily, where I actually try to expand my, so I reduce the velocity. Once I reduce the velocity, the sediment deposits and the water I can take, so upper layer I can take up here. So these are the different type of desilting basins. There are tunnels, and tunnels also have different cross sections: circular, horseshoe, and D-shaped sections, X-shaped sections. And depending on the geography, topography, or geography or geological conditions, if it is a very good rock, I can use this section, I can use this section. But if it is not a good good rocks, then I use horseshoe kind of things. So these kind of sections you can very well you can see. Then there's a 4-bay tank where water, before it enters in the penstock, water is collected there, and it gives like some kind of fluctuation it can take care of easily. So it has a basin, it has a spillway, it has a gate wall, outlet, trash rack, and also I have to collect my trash which is flowing with the water. I should not allow any trash to go to my turbine. So because my penstock starts from here, the such tanks, it's like a 4-bay tank where the surges happens because when we operate the turbines, the surge happens, and penstocks, which is a pressure flow, when it is a pressure conduit. So in the penstock, I should have a shortest possible, sharp bend should be avoided. I have to use it by grade of with the topography. I can branch them, like if I have 2 units, so I can bring one penstock and can branch them. Even 3 units, I can, with 1 unit, one penstock, I can branch into 3. But that all depends upon the local condition. For that, more detailing is required. So this is like a routing of the thing here. You can see I put it on the part. This is on surface penstock, but I also can put inside the one, and I can put vertical also. So that all depend on my local conditions. Economic diameter penstock has to be chosen, because if I do a larger diameter, then costs become high, but my losses are less. If I have a smaller diameter, then my cost of the penstock is less, but my losses become high, and loss is nothing but money. So a lot of optimization happens on this. So economic diameter of penstock happens. There are a lot of research and people keep on doing on this. So you have to take a balance on this. So economic is called economic diameter. And similarly, the material also of the penstock's material is also is taken based on the economic decision that what you should do, because different materials of the penstock, ductile iron, cement, concrete, wood shave, GRP, ultra PVC, mild steel, HDP, all that is the one where frictions, weight, corrosion, cost, jointing, pressure, etc. are important, and accordingly it has to be dealt with. Anchor blocks are the one which prevent sliding of the penstock. And it has to control the expansion and contraction of the pipes, etc. And these are used when you have exposed penstock, not otherwise. There is spillways, because if the water you are not using in the 4-way tank, water has to spill, otherwise it's going to flood the area. So those spillways are there, and there are many times this are regulated, and there are various kinds of spillways which you can define it here, because a lot of river water engineering there. Then you have powerhouse building where a structure is there, and this powerhouse building will have a where turbines is housed, generator, control panels, even so all that will house it here. So this is where you have a machine hall, then you have erection bay, the transformer, the control room. So these are the major components, but not necessarily that they have to be this way. You can have erection bay on this side, you can have control room here, you can have control on the downstream side, you can on the left side, anywhere. So this is not a sacrosanct on that side. And not only 2 units, you can have many units. Dimensioning of powerhouse, of course, related to the machines, that what kind of machines you are choosing, and you should have some safe distance in terms of working conditions, etc. And so there are classification of turbines. I'm not going to, many of you, if you are mechanical engineers or civil engineers, they might have gone through in their classes in your bachelor degrees, that there are various kinds of turbines, impulse and reactions of Francis and axial flow, and that's called Kaplan, and then in impulse, Pelton, turbo, and cross flow. So just to give an idea about it. So I'm just giving an idea, and these are already uploaded on the file site, so you can download them, and maybe our Professor Rhythm Singh will be sending you this by the mail. So these are the applicable range of their discharge, etc. And this is the flowing chart, operating range. These are the efficiency. You can see my efficiency of propeller is very low. Not the peak, but in terms of variation of the flow, the best is the Pelton, the red one. But Kaplan and Francis are also there. And in some of the areas, they are not supposed to, because Francis and Kaplan are not supposed to operate between 40 to 60%. We call them prohibited zone. So that is the time they have a lot of noise, vibration, etc. So either you operate, but you can see the efficiency drops very fast here during when it becomes lesser than 30-40%. These are the factors governing for selection of turbines: head discharge, specific speed, variation of head, maximum efficiency, part load efficiency, initial cost of civil works, number of units, running and maintenance costs, cavitation characteristics, transportation limitations. So you can see these is how to calculate the specific speeds. This is a Pelton turbine. You can do a very simple turbine, which all of us understand, because this is the one which we, this was horizontal, this is vertical, you can see here. And this is a turbo impulse where I'm not actually striking directly, but I'm starting with a angle here. And this is cross flow turbine. This is my Francis turbine. You can see here. This is you can see the penstock is coming from the bottom, and this is the transfer. Another version can be here. You can the thermistor is coming from the top. So both are the same. You can see it doesn't make a difference. So this is I just tried to say Kaplan turbine where we have these blades are here. They are fixed blades or they're rotatable blades. You can rotate them. You can also fix blade. If it is fixed blade, it's called semi-Kaplan. And then if you are moving the blade also, then it's called Kaplan in that sense. And then there are various versions of this: bulk turbine, pit turbine, S turbine, stuff flow turbine. You can see these kind of versions are there. So you can see here, same at the same unit, at the same place. I can have a bulk turbine, I can have a Kaplan. This is a vertical one, this is a horizontal one. Of course, it has a little bit of advantage that my bends are less here, so my losses will be less, so it is really more efficient, and also my excavation will be a little less. So it has advantage, but then it has a different thing that it has to be because it's a low inertia machine. So many people have studied that advantage of bulk turbines are bigger, but it has to be applied at selected places. You cannot do it with places. So these are some advantages. There are small turbines, very small turbines, like a screw type of turbines. They are, you can see, if somebody from Indore, then he can see on in Indore city itself, he has a screw turbine of 20 kilowatt scheme on wastewater treatment plant. So these are the type of generators are there, synchronous and inductions. Most of the time it is used as synchronous generator, but smaller capacity projects, even induction generator is being used because then they draw the frequency from the grid. Similarly, rotational speeds are there. So these are the frequencies depending on the, like our country has 50 hertz, but then there are some countries which have 60 hertz. So accordingly, depending on the number of poles, so those electrical engineers. Sometimes we use a speed increaser to increase my velocity, my speed of the, to match with the generator, because generator, I should choose with a higher speed because higher speed generators are less expensive and less in size and they're easy to transport. See, so I can have this flow control mechanism, which is the governing systems, which is I can have the mechanical systems. I can have mechanical means is the fluid based. Then we have the electronic systems, so mechanical, hydraulic, electrical, hydraulic, and mechanical, electrical. So, but of course, we have to use all the time mechanical, but only the controls and sensing is the one which is governing one. Let's talk a little bit cost about wise, something about 10 crore rupees per megawatt kind of cost is there. This is based on this and data about 240 power plants in India. Of you can see these are the cost range, and of course, cost is rising. So, a little bit cost keeps on rising. Similarly, for the large projects, almost same, not a big difference there. If I just to have a low head and high head, if low head is there, then my cost is relatively, capital cost relatively low, but then I have relatively, lesser electricity. So it's all depends. High head normally, these figures are not sacrosanct. This can side to side condition. Recent technology out there, we have making a lot of efforts in efficiency. So those who are interested in doing the research, there's a lot of scope in doing the research, maintenance, so that my maintenance cost is reduced, my life is increased, my utilization of water and more efficiently, and especially we have a conflict demand. So new materials are being used, resistive materials, so new designs, new softwares. So there are a lot of things. I'd like to spend 3 minutes about it. I don't know whether Ridhav has mentioned or not. We have in our department a simulator, real-time simulator for hydropower plant, which actually simulate for Francis turbine and Kaplan turbines. So this has been commissioned where a lot of training is being imparted. We also have independent turbine laboratories where we model, we create. This is as per IC. IC is the international brand, international standard, and this is as per ISO, and it is duly credited by NABL. So this is we operating for the last 2 years. We also keep on having a lot of evaluation of the hydropower plant, performance evaluation, where efficiency testing done at the sites. So about 250 plants all over the country have been done. We also have a sediment monitoring laboratory where sediment erosion measurement at site, measurement in the laboratory, different kind of online instrument for sediment measurements, which goes and impact the turbines and other parts. We have a one of the unique laboratory we have maintained. We keep a lot of intensive training. We also have another portfolio of environmental management of rivers and lakes. So a lot of work has been done on that. And there are a lot of guidelines we have issued. So those who can browse our website under the publications, you will find a lot of guidelines available, standards available. So they can use many things, especially for management on this. So this is which I just in the last few slides I was very rapid because of these are more informative and we can debate. So now I will I'll close my presentation and I'll unshare it now. And after this, I will be now requesting you to come for discussions, because discussions is a part of our this question answer. So please go ahead. So you can unmute those who want to speak on that. You can unmute and then you can ask me.
Good morning, sir.
Yes, please.
You mentioned about desilting in the hydropower plants.
Yes.
So generally in the northern part of India, the turbine blades are getting failed because of the silting, the small size silt. So what could be the new technology possible which can avoid the failure of this turbine blades, which is quickly became failure because of this?
First of all, I would not like to use the word fail word. They get eroded. Erosion and fail is a different thing. Turbines do not normally fail it. It's very maybe once a blue moon that turbine will fail. It's a fail means that means you are not genetic. It doesn't happen like this. The turbine get eroded because there is a abrasive erosion because of silt. Now there are three things. One, we have to make efforts of reduction of the silt. So there are management in the watershed, so that watershed if is managed, you will be having lesser silt coming in the water. Second thing, you must have an efficient desilting arrangement, so that silt which comes along with the water in the channel or a tunnel is desilted. And third important thing which is coming up, that we are developing silt resistive material. Silt resistive material. By either material is silt resistive or we are applying coating, which is very hard, which will be able to withstand the abrasion. So for that reason, we are, and there are, these coatings are expensive, normally done by the robots, and these are specialized field. And also in coating, please understand, once you do the coating, does not mean that it will not erode. It will not have a abrasion. The abrasion may be there, but then duration, like for example, if it happens, there are cases where erosion happens in one season itself. When I say one season, that means every monsoon season. But then there are plants where the abrasion does not happen forever, especially in southern India and central India, where this silt is not that big issue. And where we have a very good dam, and if you have very good dam, and from the dam all silt is being deposited there. So, but then this coating will be able to reduce your rather increase your repair time or maintenance time. So like suppose you are happening every year, that will reduce to say once in 2 years, once in 3 years. So that will happen. But then a lot of power plant like Lafla Jhakri has now placed a coating plant right there, power plant itself. So that because there's a lot of stakes are very high, they could afford the cost, they are doing it. So this is the way we can handle the. One more thing, if you are from northern state, are you from northeastern state?
No, I'm from Gujarat.
Okay, Gujarat, that's not an issue. Gujarat is water is relatively silt is not an issue, and silt is not an issue in Gujarat much. No, not at all. Because most of the time you have a dam-based schemes where all the sediment which comes, it is deposited in the sediment in the one, and you have very fine particles going along with the water, and that is not an issue. Yes, please. Anybody else, please? I will welcome the questions, please. Not only one question. I have to ask, have you seen hydropower plant yourself? I hope everybody might have seen the plant. Have you noticed any peculiar thing? Or what is your view about hydropower plant? So please, anybody speak on this. You need to speak, Ba.
Sir.
Yes.
I am Kumar. Sir, I asked a question. Minimum height is required to produce commercially hydropower generation.
Okay. You see, if you have a 2 meter head, 2-meter head has been
Yes, sir.
2-meter head has been one of there are more than 20-30 projects where 2-meter head been used in canal falls. But then there are projects which even less than 1 meter, 2-meter also there. But in terms of technology, I would say commercially, 2-meter is I would like to have a 2-meter, minimum 2-meter. Beyond that, it's wonderful, no issue. Because most of the turbine manufacturer manufacture their turbines with 2-meter head. But there are, if there are situations there where the turbines can be made, no issue.
Thank you, sir.
Yes, please.
Yes.
My dear, I'm not able to hear you. My dear, I'm not able to hear you. So I don't know what to do because because my Microsoft team is in progress, though it's saying progress, but it is not responding. It's all going there. So I'm not able to hear you at all. So what I'll do, I should do what I should do. You are able to hear me?
Yes, sir. Yes.
No, but there's a lot of cracking is there. A lot of cracking is there. I don't know why. So I kept this session for this only. You have to allow me. I will take it out myself and no. Oh, yeah, I can take it out myself because I'm not able to hear you at all. So and my system is hanged now.
Okay.
No, I'm not able to hear you. Sorry guys, this is the somehow it happened that my system hanged, but now I'll come back. So please ask the question now. Hello? You can unmute yourself and ask the question, please. Can you hear me, please? Hello, Priya. Can you hear me? Hello. Hello? Yeah. Can you ask the question, please? I'm waiting for the question.
Hello everyone. You can ask
Yes.
question from Arun sir.
If there is no, I would like to say that you have seen any Hydropower project. Dr. Selvan, have you seen a project? Dr. Kar, Sanjeev Kar? Hello, Mohammad Nair Alam? Okay, so since there is no question and there is no thing on chat box also, is there nothing on chat box? Hello. Priya, am I audible?
Yes sir, you are audible.
Okay, fine. So if there is no question, so we can switch it off now.
Okay.
Any question, please? Any clarification? All right. So I think thank you very much for your participation.
Yes, thank you so much sir for such a wonderful and very informative session. So we are taking a tea break now, and next we will meet again at 11:30 for the next session, that is modeling and simulation of hydropower systems. So okay, thank you very much everyone. We will meet at 11:30.
Thank you, madam.